What I want to do today is I want to give a talk on Benford's law of digit bias. This is one of my favorite subjects. It's wonderful in terms of both having applications as well as having a lot of really good theory. Most of the time when I give talks on this, I'm actually not able to go deeply into the theory because I don't have an audience that is extensively prepared in probability. So these are actually slides from when I returned to Brown, where I was a postdoc for 4 years, and I taught a class on mathematical statistics. So it was a very fast-paced class using a little bit of both. And so what I want to do today is go through some of the general theory of Benford's law. Why is it useful? How does it review all the different stuff we've been covering over the semester? Again, continuing our theme of let's review what we've done and see why it's useful. And talk a little bit about maybe opportunities for future research. A lot of this stuff is joint with students of mine, either students at Williams or students at Brown, students from the summer program. In the interest of space, I'm probably going to mostly talk about some of the work I did with students from Brown, because, well, I'm busy at the end of the semester as well. I'm going to use the slides from when I went to Brown. It's not surprising who I would want to highlight when I'm speaking at Brown. But the main reason is I want to really talk about convolutions of random variables, about sums of random variables. And that was work I had done with students at Brown. Some of the stuff I've done with students at Williams is fragmentation processes, both with physics as well as math students here. But that doesn't really fit in as well with the stuff we're doing this semester, which is why the emphasis is more on the Brown stuff. Okay, so here is what I consider an interesting question. For a nice data set, and nice is the standard math term for something that we think will behave well, and we'll just put on whatever conditions we need as time passes. Fibonacci numbers, stock prices, chemistry addresses of Math 161 students, what percentage of the leading digits are 1? So if you've never heard of Benford's law, if you just had to guess, if you had a data set, how often would you say the first digit of numbers is 1? Would be the most intuitive thing to guess. 10%. And then you realize you had a brain freeze, and it can't be 10%, and you correct to 11%, because no leading digit is going to be a 0 unless the number is exactly 0. The actual answer is about 30%. So the first time you see this, hopefully it's surprising. There's this profound bias. You have this tendency to having low leading digits. It turns out that there's a really good explanation as to why this is the case. If you look at numbers the right way, oh, wait, I don't know if this is on. So I'm not sure if this is recording, so let me try this. I'm not seeing the lights going, so let me try this again. Almost made it through a whole semester without too much technology failures. Alright, there we go. Now it's working. Alright, so there's a reason why in a lot of natural data sets you have this bias towards having small leading digits of 1. And it turns out if you look at numbers the right way, and I will show you the right way to look at numbers, the bias actually disappears. And the numbers are, in some sense, uniformly equidistributed, but your notion of what uniformly distributed changes a little bit. This is similar to a lot of things we've done where we've done change of variables, and rather than looking at one variable, we look at another variable. You've seen this in calculus when you're trying to do integration. We saw this with the log normal distribution. We had a 1 over squared of 2 pi x squared e to the negative log squared of x over 2. This was a beast to deal with, an exponential of a log squared. But the reason it's called the log normal is it is related to the normal distribution. So let me just shift this back in so that it's all in focus. All right. So I want to quickly state Benford's law, talk a little bit about the other reason for using these slides from when I gave it at Brown is the recording I know from that one worked well, and so in an emergency I can always give that to the students who are taking this remotely. All right. All right, so I want to discuss some examples and applications, sketch some of the proofs, and if possible, talk about some open problems at the end. If any of you are looking for research projects or theses, I have several really good questions along these lines that I would be happy to chat about. All right, so just a couple of caveats. We're going to be talking about using Benford's law of digit bias to detect tax fraud and questions like that. Just because you have a test that indicates that something suspicious may be happening does not mean that something suspicious is actually happening. There are alternative explanations. One of them could be that this camera is no longer working. And so I'm just trying to, and I apologize for this. I'm just trying to see if I can actually get this to work and record.
And it does not seem like it's going to be able to. So I'll try one more time, and then I will just give up. And then the people who are taking this remotely will suffer. Well, they can watch the slides. They can go through the slides at home. The slides are online. They can go through slide by slide. All right. So here's one of my favorite Dilbert strips, especially since I've had so many of my expenses rejected by Williams College, including an expense for under $7 for a lunch buffet because it was not properly itemized. I did not tell Williams what I ate at a lunch buffet. And for those of you who took a Lego winter study with me, this is actually what caused me to create that winter study, is I figured, well, what could I itemize? And so you're either a liar or worse. I decided what to order based on what totals to a round number after 15% tip. That's worse. You do have to remember that just because something indicates that maybe something suspicious or nefarious is happening, that is not proof. Okay, so here is finally a statement of Benford's law. For many data sets, the probability of observing a first digit of d base b is log base b of d plus 1 over d. Most of the time we're going to look at things base 10, so you'll take b equals 10. So base 10, about 30% of the time you get a 1, about 4.5% of the time you get a 9. Not all data sets satisfy Benford's law. So here's a really good example of one that does not. So imagine you have a long street where the houses are boringly labeled 1, 2, 3, all the way up to L. And you want to ask what percent of the first digits are 1. Well, it's going to make a huge difference where you stop. If you stop at street 199, you've just gone through 100 houses with first digit 1. If you stop at street 999, you've just gone through an enormous run of streets that do not, of houses that do not start with a 1. And in fact, you can oscillate between essentially 1/9 and 5/9 with first digit 1, depending on where you stop. Now, where you get Benford is that not all streets have the same length. And so if you were to take all of our houses here, and maybe what I'll do is I'll have everybody email me their street number and where they live, not on Williams campus, because there will be high dependencies there, but if you have a lot of different streets of a lot of different lengths, and you look at the leading digits of the houses in that sense, that will be a pretty good approximation to Benford. The general philosophy is the more averaging you have, the more mixing you have, the closer you're going to get to Benford. And we will see why this is true. Does this remind you of any theme we've seen this semester? Where the more of something you have, the more smoothed out the behavior is. The central limit. The central limit theme is actually lurking in the background. Now the central limit theme does not initially look like Benford's law. We're going to see today how they're connected. As I talked about many different streets. So here's a couple of examples of places where Benford's law occurs. Recurrence relations. So we'll talk a little bit about those. We did that very early in the semester with Benet's formula, the Fibonacci numbers. These are used to model a lot of processes in the real world. Because difference equations are discrete versions of differential equations, if they satisfy Benford's law, this gives you an idea that maybe Benford's law is going to be widely applicable. Special functions, iterates of power, exponential rational maps, products of random variables, a bunch of other things. Order statistics, we talked a little bit about order statistics with the coin problem recently. Hydrology and financial data, and many hierarchical Bayesian models. So there's lots of different places where Benford's law emerges. I am a number theorist. I don't know if I can go an entire class without talking about the Riemann zeta function. I made it, I think, almost to the end of 341. This is one of the most important functions in all mathematics, the Riemann zeta function. So again, in complex analysis and number theory, you'd study this in greater detail. It's defined as the sum of 1 over n to the s, n goes from 1 to infinity. It's the same as the product over all primes of 1 minus 1 over p to the s inverse. One way to prove this, when the real part of s is greater than 1, is use the geometric series formula to expand the right-hand side, and then you multiply everything out, and you use unique factorization. Every number can be written uniquely as a product of prime powers. This, in fact, is why we do not consider 1 to be a prime number, because if 1 were prime, we would not have unique factorization. I could write 6 as 1 to the 2015 times 2 times 3, or 1 to the 11 times 2 times 3, or even just 2 times 3. By assuming that primes start with 2, by defining them that way, we now have unique factorization. The reason this is so useful is the following. Can somebody tell me what the next integer is after 2015? Yeah, it was a little slow, guys. The next prime after 2015. And I'm happy with you having a little bit more thought on that one. The distribution of the integers is not that mysterious. I know everything about how the integers are distributed. I know how long I have to wait on average from one integer to the next. I know the fluctuations about the mean. There's really no
uncertainty. There's no surprises in how the integers are distributed. How the primes lie, very different story. The idea is we want to use knowledge of the integers to get knowledge of the primes. And so, for instance, if you take the limit as s goes to 1 from above, you get the harmonic series. What do we know about the sum of the harmonic series? It diverges. If there were only finitely many primes, the product would be finite as s goes to 1. There must be infinitely many primes. This is just the beginning of how important the Riemann zeta function is to studying the primes. So what I did is I looked at, it turns out you can extend this from when s equals something less than 1, whose real part is less than 1. We talked a little bit about this when we looked at the geometric series. We had 1 plus r squared plus r cubed. This makes sense if the absolute value of r is less than 1. If the absolute value of r is greater than 1, that sum doesn't make sense, but the formula 1 over 1 minus r does make sense. This is called analytic continuation. We can do the same thing here. It turns out the most important values of the Riemann zeta function are on the critical line, real part of s equals 1/2. I looked at about 65,000 values at 1/2 plus I k over 4. And here is a plot. Either the diamond is the Riemann zeta function and the star is Benford or vice versa. I forget which is which. Why do I not care?
They're so close.
Yeah, they're so close. I mean, the fit is phenomenal. And so this was one of the first papers I ever wrote was on why we have this agreement. And I did this for this and the 3x plus 1 problem with a colleague of mine who were both at a conference in Hawaii, and we felt guilty that we were basically using all this grant money to go to Hawaii, so we felt we should write a paper. Then we went back to going to the beach. Okay, so math and stats can be fun. The conference was called the International Conference on Statistics in Honolulu or in Hawaii. They made sure Honolulu or Hawaii was in the name of the conference, so it was quite clear what was going on. The hotel was on, I know this is being recorded, the hotel was on the beach with glass windows. It's a great conference. So here are some applications of Benford's laws to why do we care, other than getting to go to exciting locations. So analyzing round-off errors. For those of you in computer science, when your computer's doing calculations, errors can accumulate. This is a great application. Determining the optimal ways to store numbers. The most important is detecting tax and image fraud and data integrity. Years ago, actually it was so long ago that the Red Sox were bad, I was watching the news the next night after one of the games, and they were showing some highlights. And then there was a small controversy in the newspapers the next day because one of the networks had broadcast the game and another network was showing clips, and they had edited out all of the promotional stuff that was physically at the park from the network that was broadcasting the game. They had doctored the image without saying that they were doing that. So can you tell if an image has been doctored? Why might you care if an image has been doctored? Can anybody give me any reasons?
Images are sometimes used as evidence.
Images are sometimes used as evidence, and if an image has been doctored, then that's important to know. There's another reason why you might care.
Like legal issues, I can imagine.
So one is legal issues that you've changed someone's property, but in a post-9/11 world, 9/11 world, there's another reason why you might care if an image has been doctored. Embedded messages. You can actually change, if you look at a bitmap of an image, if you change the final bits, you're not going to, of the colors of each square, you're not going to really see a difference. But you can secretly hide messages in images this way. And so the question is, can you tell if an image has been doctored? And so I've done some work with a couple of electrical engineers on precisely this problem of using Benford's law to tell has an image been modified. This is a very good way for people to leave messages in public places. Because if you're communicating with somebody, hey, we've noticed a lot of chatter with, I don't know, let's choose a country at random, say Iran, and North Korea, and Joe Schmo. I wonder what they're trying to tell Joe Schmo. Whereas if you just post an image on the web, which anybody can download, and you don't know which is the image that has the message, it's much easier to send a secret message. So in terms of applications of stuff like this is huge. For the IRS, they use this to detect tax fraud. There's a lot of companies. Which companies should be audited? There are different methods people use. One is to look at the political persuasion of the party. I would like to advocate a better way is to look at mathematics. Can you do a quick and easy test to see which company is likely to be cheating? Fortunately or unfortunately, there's not enough data on an individual tax return to really get a sense of whether or not you're cheating. There's not enough independent numbers, but for a large corporation there is. You might remember early in the semester we did a medical problem. You have a very rare disease and you have a test and you have the false positive and the false negative, and if it turns out that you come back with you've got the disease, should you panic? No, if the disease is really rare, it's more likely than not that it was just a bad test. What do we do in that case? Test again. How do we test again?
Better test.
With a better, more expensive test. We don't want to give the expensive test to everyone. Okay, we don't have the resources. So we do a way of quickly getting a sense of what is the best way to use our resources. This is great for the IRS. They can quickly determine what is the most likely situation to get the best bang for their buck in investigating. And this allows them to allocate their resources extremely well. I cannot say who, but I know somebody who works at an accounting firm where they actually do BenfordLaw tests on data before they submit returns to the government. And if there is, well, 1 second. All right, let's talk a little bit about the general theory. So just some notation. So the mantissa is given any positive number x. I can write x as the mantissa or the significand of x times 10 to the k, where k is some integer. So two numbers have the same mantissas or the same significand. You can use either language if and only if they have the same leading digits. So think of 3.14 and 314. They have the same mantissa, 3.14, but they differ in how many zeros we're padding with. Okay? So the key observation is if I take the logarithm of my two numbers base 10 and I look at the modulo 1, so modulo 1 means two numbers are the same if they differ by a multiple, by an integer multiple of 1. You are all used to doing modular arithmetic on the clock. It's roughly 10 o'clock now. What time will it be in 5 hours? 3. So you all agree that 10 plus 5 is 3. In abstract algebra you learn yes, on a clock, mod 12, that is correct because 10 plus 5, 15, and 3 differ by an integer multiple of 12. So in some sense, 15 and 3 are equivalent numbers. And so we say they agree mod 1. They're not equal, but for all the purposes we're considering, they're indistinguishable. So over here, when we look at the two numbers, when we look at their logarithms mod 1, well, when I take the logarithm, I get the log of the mantissa plus the log of 10 to the k. I'm using the log of the product as the sum of the logs. Well, what's the log of 10 to the k? It's k, the log of 10. Since I'm working base 10, the log of 10, base 10 is 1, so I get k. So the two numbers, they differ by an integer. Well, the mod 1 just chops off the integer part. So what this is telling us is this is a great transform to do, that if I want to study two numbers, it's enough to study just the logarithms modulo 1. Alright, so the idea that we need now is this idea called equidistribution. So we say a sequence is equidistributed mod 1 if the probability that it lands in the subinterval AB of 0, 1 tends to b minus a. So in other words, if I count the first big N occurrences in my sequence, I see how often are they in the interval AB, I divide by n, in the limit that should go to b minus a. So half the time I should be in the interval 0, 1/2, a third of the time I should be in the interval 1/3, 2/3. Okay? So the question is when a sequence is equidistributed. This is very close to the idea of uniform distribution, which we've talked a lot about. So here's a beautiful theorem. Professor Silva and I would prove this theorem differently. He does a ergodic theory, he would give an ergodic theory proof. I'm a number theorist, I would do a number theory proof. As this class is neither number theory nor ergodic theory, I will just state the result. If beta is an irrational number, so beta is not in the queue of rational numbers, then n beta is equidistributed mod 1. So the first thing to ask is, well, what would happen if beta was rational? So imagine beta is 1/5. And I'm going to look at the fractional parts of n times 1/5 mod 1. So I have 1/5, 2/5, 3/5, 4/5. What's 5/5 mod 1? What's 6/5 mod 1? 1/5. It just cycles through those 5 values. So if beta is a rational number, I'm only going to cycle through finitely many values. It's not going to be equidistributed. In fact, if I choose any interval that doesn't contain one of those finitely many values, I'll have no occurrences. The miracle is that as long as you stay away from that problem, everything else is equidistributed. So here's some examples. The log of 2 base 10 is irrational, and the log of the golden mean base 10 is irrational. So let's prove that the log of base 2 is irrational. If it was rational, I could write 2 as 10 to the p over q. I raise both sides to the qth power. Well, 10 is the same as 2 times 5, so when I simplify, I get 2 to the q minus p equals 5 to the p. Well, 5 is odd, 2 is even. The only way this can work is if they're both raised to the 0th power, which means p is 0 and q is 0, and so that means 2 is 10 to the 0 over 0. Well, if I'm assuming it's rational, it's not on the form 0 over 0. So the log of 2 base 10 is irrational. A little bit more work gives you the log of the golden mean is irrational. Alright, so because I'm not doing simulations live, I had to choose a number ahead of time. I chose the square root of pi, it's one of my favorite numbers. I looked at, is it equidistributed? Is n times the square root of pi equidistributed? So look at the first 10 values. Does that look good or bad? Nice. Look, how often is it in intervals of length 1/10, 0 to 1/10, 1/10 to 2/10, 2/10 to 3/10? Good fit or bad fit? Okay. Well, I figured if I gave you a number that was perfect, you'd think I cooked it up. So I had to look for a number where it wasn't perfect. Yeah, there's got to be some fluctuations, or if my data looks too good, I'm probably cheating. Now let's look at the first 100, first 1,000, first 10,000. If you have really good eyesight, you can see small fluctuations. So the question is, how quickly does it set into equidistribution? That's going to be extremely important for the IRS. So here's the fundamental equivalence in Benford's law. So a data set is Benford base B if and only if the logarithms are equidistributed mod 1. And let me show you why this is true. So let's look at the interval 0, 1. So when I look at the logarithms mod 1, they lie in this interval 0, 1. Let's look at all the numbers from 0 to the log of 2 base 10. When I exponentiate, what's 10 to the 0? 1. What? Yes. Good. What's 10 to the 1? What's 10 to the log of 2 base 10? 2. I'm raising 10 by the power of 10 I need to get 2. So everything in the interval from 0 to the log of 2 base 10, I'm just using the change of base formula to write it, exponentiates to having a leading digit of 1. So if I fall uniformly in the top, when I exponentiate, I'm going to be a bias in having a first digit of 1. Anybody know roughly what the log of 2 base 10 is?
It's like 30%.
Yes, about 30%. Yeah. And that's where the benefit comes from. If you take the logarithms of numbers that are well distributed, modulo 1, you will get something that's uniformly distributed. And the benefitness vanishes. Now most of us are not going to take logarithms of numbers base 10 and then chop off the integer parts. That's just not how we look at things. Also, certain data sets should not be Benford. If I look at batting averages, do I expect to see batting averages to be Benford for leading digits? No. It's very rare in the major leagues to have somebody with a batting average still in the 1s and survive. Maybe on the Red Sox this year you'll have some of that, but most of the time your batting average will start with a 2, or if you're really good with a 3. It's been a long time since someone has started with a 4 deep in the season. Things are too concentrated. But in general, if you have a process that spreads out naturally, you do expect to see Benford, and if you do this log transformation, it will now look uniform. So 2 to the n is actually Benford base 10, and the reason is if I take the log of 2 to the n, I get n the log of 2 base 10. The log of 2 base 10 is irrational, and we just showed, Konicus theorem, that if beta is irrational, n beta mod 1 is equidistributed. A sequence is Benford if and only if its logarithms mod 1 are equidistributed, so 2 to the n is Benford. Let's do a more interesting one. Let's do the Fibonacci numbers. I want to tie everything together that we've been doing all semester. So here's the Fibonacci relationship. We guess an is out of the n, as we did this earlier in the semester. I'm going to breeze through this. We get our characteristic polynomial. We get r squared is r plus 1. The roots are 1 plus or minus root 5 over 2. The general solution, it turns out if r1 to the n is a solution and r2 to the n is a solution, any linear combination of them is a solution. This is a really good algebra exercise to go through and check this. If you then put your first Fibonacci numbers as 0 and 1, you get the values of C1 and C2, and you get Benet's formula. The 1 over root 5, 1 plus root 5 over 2 to the n, minus 1 over root 5, 1 minus root 5 over 2 to the n. As n gets very, very large, this number is less than 1 in absolute value. As I raise it to the nth power, it's going to tend to 0. So essentially, my Fibonacci number is essentially 1 over root 5 times the golden mean to the n. If I now look at the logarithm of base 10, the log of a product is the sum of the logs. Well, the log of 1 over root 5 is a fixed shift. It's not going to affect equidistribution, and I'll get n times the log of the golden mean. We just claimed that the log of the golden mean is irrational, so by Kroneker's theorem this is equidistributed, so by the fundamental equivalence we have Benford. The Fibonacci numbers are Benford. If you get bored in today's lecture or later today, start writing down Fibonacci numbers and see what fraction of the time you get a 1. It will very quickly approach 30%. It's amazing how fast it goes. To make this a rigorous proof, you have to deal with the fact that this number is actually here. And you have to see, well, how many numbers can this change things by? It's a little tedious, it's not horrible. If anybody's interested, I'm happy to share the analysis of that. Most linear recurrence relations are actually Benford. So we saw a n plus 1 is 2 to the n is Benford. But if I do 2 to the n minus a n minus 1, this is not Benford. So if I choose the first two terms to be 0 and 1, it turns out all the terms of my sequence goes 0, 1, 2, 3, 4, 5, 6, 7. And I'm back to my street addresses. If I choose the first two terms of my sequence to be 1, the next term will be 1 and you'll get 1, 1, 1, 1, 1, 1, 1. What goes wrong is when you do the characteristic polynomial, when you try a n is r to the n, you get a repeated root of 1. And when you look at this now, we're getting 1 to the n. This is where problems are coming. Most of the time this won't happen, but I wanted to just alert you to the fact that it's not always Benford. Some issues can happen. Alright, so let's look at 2 to the n, because we've said 2 to the n is Benford, so let's look at some values. So I'm looking at the first 60, but as the numbers are getting large, I'm only going to display the first 30. So here at the first 60 numbers, I look at how many times I get a first digit of 1 through 9. Here's the observed probability, here's the Benford probabilities. I've hopefully proved to you that in the limit it's Benford. Good fit or bad fit? Looks pretty reasonable. Definitely gives us a strong incentive for taking a stats class so we can do something a little bit better than looks good. Where do you think the fit looks exceptionally good? Where do you think it's really, really good?
For 1.
Yeah, I'm doing a pretty good job on 1. 0.300 versus 0.301. Where am I having some issues? What would you say is the worst one?
9.
I would say 9, because the amount that I'm off by percentage-wise I think is the greatest at 9. And so one of the reasons that there are problems here is we have 30% of our mass is supposed to be with a 1. Over here we only have about 5%. So if I actually amalgamate say the 7, 8s, and 9s, then actually things are pretty good. Now I've got 0.33, 8317, 58, 51, 46. It's not so bad now. And so the problem is, and this is extremely important, if you have very rare events, if you don't have a lot of data, the fit's not going to be so good. It's not a really good idea to be doing this comparison. The number of recurrences I'm expecting is so small that just having 1 or 2 extra things. So back in 2004, the Red Sox did something in baseball that no team had ever done. What was it that the Red Sox did? Yes? Yeah.
They came back from being down 3-0.
They came back from being down 3-0 in a best-of-7 series. There had only been about 25 times this had happened in Major League Baseball history. Assuming the teams are equal, how likely do you expect someone to come down in a best-of-7 down 3 games? How many times do you expect that to happen? 1 out of how many?
Given they're down 3-0.
Given they're down
Yeah.
3-0,
116.
1 out of 16 if the 2 teams are equal. Do you think the 2 teams are equal? No, there's probably a reason you're down 3 games. Alright? But if you assume the teams are equal, it should happen about once every 16 times. The fact that we had 25 times it had never happened, we were only expecting it to happen between 1 and 2 times. And so to talk about how phenomenal it was that the Red Sox did this, great, but we're not expecting that many occurrences. And we're not even sure that we should consider it a 50-50 chance for each remaining game. So you've got to be very careful. Now, there's another reason to believe what's going on here. It comes from the fact that computer scientists do not know Greek or Latin. Neither do I. Is mega and giga, are these Greek or Latin? One of them. Some dead language. Alright. How many gigabytes are in a megabyte? It's not 1,000 megabytes in a gigabyte. It's 1,024. And the reason is computers work very well in base 2. 2 to the 10 is almost 1,000. So they've adopted the nomenclature of giga and mega. If it was exactly the same, if 2 to the 10 was exactly 1,000, then every time I went 10 further in my sequence to the end, I would be where I was in the beginning, padded by 3 zeros. The fact that I'm not padded by 3 zeros is extremely important. Yes?
So, just to clarify, the difference in accuracy between like digit 9 versus say digit 6 is just purely because of the number you have.
It's tough to say purely because I can always jiggle things a little bit, but I'm not surprised that 9 is so bad because I have the fewest events here. Now, I mean, it's not statistically, it's not a huge amount of difference between 6s and 9s. But what I should really be doing is I really should be amalgamating a bunch of these so I have roughly equal probabilities. Here I've got 30% in the beginning, and I'm talking about 4.5%.
Yeah.
I don't expect as good of a fit with 4.5% of my data as with 30% of my data. So if 2 to the 10 was exactly 1,000, every time I iterate 10 times, I would just pad 3 zeros. And if you look, there's a reason why I wrote the numbers as I did. You can see, look, I started 8, 8192, 838, 512, 524, 536. I'm almost pi. That extra, very small, 2%, it takes a while to accumulate. And in fact, we don't see any numbers that start with a 7 in the first 30. It takes a while for this to come into play. So what I did now is I looked at a couple of different numbers that are irrational. I looked at gamma, which is a very famous constant, the Euler-Mascheroni constant. I looked at E, and I looked at pi. And there's a test in statistics called the chi-squared test. The smaller the chi-squared value, the better fit you have between your theory and your observed data. And so 95% of the time, I should get a chi-squared value of 15.5 or lower if Benford's law is really describing the powers of alpha to the n for these 3 alphas. Which one looks different from the others? Which one looks like I'm having some issues? Pi. Pi does not look nearly as good. It starts off high, it's getting lower, so you think, okay, maybe everything is finally good now. Nope, jumps up enormously. So there's always at least 1 or 2 math geeks who can rattle off digits of pi. Do I have anybody here who can rattle off some digits of pi?
3.
Wow, standards have gone down in my 7 years.
1, 4, 1, 5, 9, 2, 6.
5. Any more? 3, 5. Anybody rattle off digits of pi squared? Pi cubed? Modern education. So, if you really do your powers of pi, and you got to pi to the 175, you would notice that pi to the 175 is approximately 1.0028 times 10 to the 87. So every time you increase by 175, it's almost as if you've appended 87 zeros. Because pi has such fluctuations in its chi-squared statistic, a big point I've been trying to emphasize in this class is how do you present data. So I'm not plotting the chi-squared values on the vertical axis, I'm plotting the log of the chi-squared values. If you notice, if you look at the red, which is the pi, its chi-squared values, it looks periodic. The amplitude seems to be decreasing as I go further down. Anybody want to roughly guess what the period is? It looks damn close to 175. Here's 200, it's hitting a little bit before 200. You can see in the data the fact that pi to the 175 or something around then might be very close to a integral power of 10. And when I'm trying to see how rapidly things converge, pi is going to have slower convergence than other numbers because a high power of pi is very close to a high power of 10. If you find stuff like this interesting, Professor Gowdy is teaching a class on continued fractions next year, which will talk about issues like this and others. Applications. So I'm not going to go into detail. This is from somebody named William J., married to somebody named Hillary from Arkansas, has 1 daughter. One of my colleagues says it is amazing what the Freedom of Information Act will get you. Alright, so I'll let you look at those later. This is one of my favorite examples. An audit of a bank revealed a huge spike of numbers starting with a certain digit more than you would expect according to Benford's law. Any thoughts as to what that digit was?
2.
Nope. Nope. Nope.
4.
Yes, 4. Excellent. A lot of them starting with 4s. Any thoughts as to what the second digit was? There was a little bit of a spike. It was 4 what?
9.
Yeah, 4, 9, and 4, 8. And they traced this. And they were getting a small number of 4, 8s and 4, 9s more than they expected, and they traced it to one person. And this person was responsible for an enormous amount of entries with 4, 8s and 4, 9s. Has anybody ever lost a credit card? Okay, what happens when you lose a credit card?
You have to go and cancel it.
Okay, and did you have to pay for all the stuff that was charged?
No,
No.
because.
So what happens? So this, if you've seen Seinfeld, there's a great, skit on the bank writes it off. Okay. Now now imagine you're the bank, you're the credit card company, and somebody reports a credit card stolen, and there's $25.13 in disputed charges. Is it worth having an investigator try to track down the people who stole the credit card? Imagine there's $95,000 in charges. So where do you draw the line? Any thoughts?
Isn't it anything like 5,000?
It's 5,000. So the write-off was $5,000. And so the way the bank worked is anything above $5,000 was investigated. Anything below $5,000, the person on the phone could just write off. You lost your credit card? Oh, I'm so sorry to hear that. Don't worry, we'll take care of everything. So this person was having his friends get credit cards, run up debts close to the limit, and then call in and report the card stolen. And they caught this person using Benford's Law. Now what you should do, I'm sorry, this is being recorded. If you wanted to cheat, you need to make sure that you don't always do the same numbers. If you're the bank, what you should do is you should say, we will always invest anything above $5,000. Anything from $4,000 to $5,000, maybe we'll investigate 80% of the time. And you have something like this, so nobody is ever safe. What this means is when you're trying to decide whom to check, say at airport security, 95-year-old grandma in a walker will occasionally be called over and searched. If you don't do that, people know this is a protected group, I'll disguise myself as an 80-year-old grandma. But you probably don't pull over 80-year-old grandmas all the time. You probably concentrate on other categories. It's how do you use finite resources. This is a great thing about Benford's Law. Alright, here is stream flow data. There's 130 years worth of this over almost 500,000 entries. And you see incredible agreement with Benford's Law. The statistical analysis of this is actually difficult because the data set is so large. The chi-squared test, for those of you who know statistics, actually returned it's not a significant fit because we have so much data. You have to do other, more sophisticated tests. I want you to be aware of things like this. Visually, however, it's a great fit, and I'm happy to leave it at that. I'm not going to talk about election fraud and Iran. They're our friends now, or soon to be. I will move on to products of random variables because this is a class in probability, and I can finally talk about stuff like this. Alright, so let's imagine we have a product of random variables. We have mostly been working with sums, okay? But I'm not even going to bother asking you what to do because it's automatic now. Whenever you have a product, you take a logarithm. If you learn nothing else from this class, at least please take away that. Modulo, when have I told you not to take logarithms? What's the one time I've told you not to take logarithms of products? When you're teaching elementary school kids mathematics. Okay? Resist the temptations there, okay? Other than that, take logarithms. If you've got a product and you want to understand the product, take the logarithm. So I've got the product of x1 through xn. That's the same as understanding y1 plus dot dot plus yn. And if I want to understand whether or not something is Benford, I don't really care about the full distribution of the product. I only care about the distribution of its mantissa. So when I look at the sum of its logarithms, I only need to understand that modulo 1. Well, let's say the density of yi is given by gi, then the density of yi plus yj is given by a convolution. I will define later what the Fourier transform is. For now, it just means put a hat on a function, and that's called the Fourier transform. It's related to the moment generating function. It always exists. And the wonderful fact is the Fourier transform of a convolution is the product of the Fourier transform. So here, if I call Hn the density of the sum of the ny's, the Fourier transform of H is the product of the Fourier transform of the g's. Which would you rather do, multiply or do integral convolutions?
Integral.
Try again.
Multiply.
Multiply, right? We do not like to do integration. Integration is hard. Convolutions are hard. You saw how bad it was just adding uniform random variables. We don't want to do that. We want to multiply. This is one of the reasons why the Fourier transform is so powerful and why it should be on your radar screen. Convolutions are hard. This allows us to bypass a lot of them. And in the book, I actually go through and I prove the central limit theorem from a convolution perspective. So if you're interested in stuff like this, if you want more theory, happy to chat more. I just want to show you what's out there. So here's the theorem. Let ym be independent continuous random variables on 0, 1, not necessarily independent identically distributed random variables. Let the densities gm be, for the corresponding ym. I'm going to study the sum modulo 1. It converges to the uniform distribution as m goes to infinity in L1. That just means if I look at my density, and I look at the density of the uniform, which is 1, I look at the absolute value of their difference and I integrate it, that goes to 0. Alright, so basically the probabilities I assign on any interval a, b, the difference goes to 0 with the uniform distribution. If and only if a following condition holds about products of the Fourier transforms at certain coefficients. I'm not going to go into the proof of this in great detail. I will sketch a little bit about how this is related to the central limit there. Alright, so I'm going to skip the generalizations that's there. You can actually come up with situations where the variables are not identically distributed where you do not get Benford's law. So here's a situation where I get an incredible bias. What's interesting is if I chose any of these functions every single time and chose all my random variables identically from one of these distributions, it would be Benford. But at each m, I'm choosing a different distribution, and I'm stacking things up in such a way that the resulting thing is not Benford. Alright, so let me give you a proof of why this converges to the uniform under slightly stronger conditions. I'm going to assume y1 through ym are nice random variables, and that they converge to a Gaussian. Why should y1 plus ym converge to a Gaussian?
Central limit theorem.
Central limit theorem. So by the central limit theorem, this should converge to a Gaussian. If it converges to a Gaussian, if they're all independent identically distributed, I might as well assume they have mean 0. And what do you think is going to happen to the variance as I get larger and larger and larger? If they're all identically distributed, what do you think will happen to the variance of the sum? What do you think is going to happen to the variance of the sum? It's the sum of the variances. The variance is not going to be 0, so the sum of the variance is going to grow and grow and grow. So imagine in your mind, or sorry, on a piece of paper, you have a normal distribution, and the variance is growing. As the variance is growing, it's becoming flatter and flatter and flatter. And so if you now chop it up and look at it in intervals of length 1, it's going to look more and more uniform, and you're stacking them all together. So a uniform, or a normal with growing variance, where you then stack it up and just chop it up and keep piling it up, they're going to look identical in the limit. So the details is, here's a plot of a normal, mean 0, standard deviation 1. Here's what happens if I now look at it modulo 1. So what I did is, I take everything from 0 to 1/10, everything from 1 to 1.12 to 2.13 to 3.1, as well as negative whatever, and I pile that all up. And this is my probability distribution. Does that look uniform? Not even close. Now, however, I look at, this was standard deviation 0.1, here's standard deviation 0.5. Does that look uniform? Well, if you look at the axis of y, it goes from 1.015 at the top, 0.995 is the last one labeled, so it's probably 0.990 down below. The scale on the vertical axis is not that big. It's actually already with a standard deviation of 0.5. The standard normal, the normal is actually pretty close to uniform. And so if you go even further, it gets even better. It converges to uniform very fast. I'm not going to go through this in great detail, but this is the Fourier transform. You take your function f of x and you integrate against e to the negative 2 pi I xc dx. This looks very similar to the moment generating function. In the moment generating function, what do I integrate? I take f of x, my density, and I integrate against what? E to the tx. So instead of doing t, I'm using Lec34. Not a big deal. But I have a negative 2 pi I. The negative 2 pi is not a big deal. I can replace t with negative 2 pi t. We talked about properties of the moment generating function. We talked about, well, if you replace x with ax plus b, how that trivially changes things. The negative 2 pi is not a big deal. The big deal is I. I is the square root of negative 1. E to the minus 2 pi I xc, that always has absolute value 1. This is cosine 2 pi xc plus I sine 2 pi xc. And my function here, f of x, it's integrable. If I take absolute values, it's bounded by the absolute value of f of x. So this is still going to be integrable. This exists for every distribution. You put in a Cauchy distribution, it exists. So if you want to study an object, one of the nicest things for the object to have, one of its nicest properties, is existence. Okay? If the object does not exist, it is going to be hard to study. There's the story of somebody who did his thesis on, properties of a certain class of functions. And a few years after the person's thesis, it was discovered that the only functions that satisfy these properties are the constant functions. And all of his results were already known for the constant functions. You want to be very careful. What properties are you assuming? What is your space of discourse? Okay? So here, the Fourier transform will always exist for a probability distribution. And so when we talk about we want the moment generating function to converge, we need all the moments to exist. It turns out that just having the first 3 or 4 moments exist is sufficient. 4 moments is definitely safe enough. Maybe a little bit more than 3 suffices. So the Cauchy distribution is not going to be quite enough for us to work with, which is good because what's Cauchy plus Cauchy? Okay, so Cauchy plus Cauchy plus Cauchy? So we don't expect sums of Cauchy to converge to normal because they stay Cauchy. It's a stable distribution, right? So something should break down. Well, while the Fourier transform of the Cauchy distribution exists, we don't have finite first 4 moments. We've talked about how the shape of the distribution, we really don't see the shape until we get to the 3rd or the 4th moment. If the distribution is symmetric about the mean, it's the 4th moment that first gives us the shape. If we have finite mean and variance, I can always adjust by shifting things, by translating, by rescaling, so I have mean 0 and variance 1. So when I tell you I've got a distribution mean 15, variance 3, big deal. I have no idea what that is other than it has finite mean and variance. I can always adjust my units to make it look however I want. Once you start telling me the 3rd or the 4th moment, you now have a shape. Okay? Most of the time we only talk about the first few moments. I think in my life I've only seen the 3rd and the 4th moment explicitly used once outside of a math class or math paper. I was visiting a friend of mine at Harvard. She was taking a physics class populated by a lot of pre-med students, and they listed the mean on the test, the variance on the test, the kurtosis, and the skewness, the 3rd and the 4th moments, so that the extremely competitive Harvard students would know precisely where they stood relative to their classmates. This was, I think, the only time I've really seen the 3rd and the 4th moment done in public. For the most part, the 1st and the 2nd moments are known. Just like when you look at differential equations, for the most part, you only need to look at 2nd order differential equations. It's nice that this is the case. But to rigorously prove things, we really need something about the 3rd or the 4th moment to make certain arguments hold. That's damn good because the arguments should not work for the Cauchy, because Cauchy plus Cauchy is Cauchy. So again, if you don't care about Benford's law today, what we're doing right now is we are seeing how all of the stuff we've done comes back together. We've talked a lot about stable distribution. We've talked a lot about the central limit there. Benford's law, one way of viewing this is it's another manifestation of the central limit there. It's coming from products. Whenever we have a product, we want to take a logarithm, we want to get a sum. There's a normal distribution lurking in many cases. That normal distribution looks like a uniform for the case that we care about. Good tools to analyze stuff like this is Fourier transforms and this thing called the Poisson summation formula. So I'm not going to go into all this. The slides are here if you really want to see how all this is done. I don't think we really want to go through that in class now. We can always hit pause, although I don't think it's really displaying on the images there. I'm not going to go through too much of chains of random variables, but I just want to briefly say to you, because we've got about 2 minutes left, let's say we have some nice independent random variables, and I want to talk about the density of the product. So we talked a little bit about this. There's a section about this in the book now. The density of the product, it's a convolution, but it's a slightly different convolution. It's a multiplicative convolution instead of additive. Now if I take these two quantities, x over t times t, the product of those is x. This is giving me the probability that the product of 2 random variables equals x. The difficulty is now we have the measure dt over t. This might be hard, but anybody remember where we've seen something like dt over t or dx over x before? In the gamma function, excellent. When we had x to the s minus 1 dx, we can write that as x to the s dx over x. What's really going on is there's a Mellin transform lurking. The difference between Mellin transform and Fourier transform is your accent. Are you talking about the products, or are you talking about the logarithms? And you can pass from one to the other. It's a question of where do you want to study, where do you want to do the algebra. This is a major theme of the class. What's the best place to do the algebra? And so I'm not going to go through, there's all the different stuff you can get. All this stuff holds for subsequent variables. I just wanted to quickly jump to conclusions that we want to develop more sophisticated tests for fraud. So I actually gave a talk on Benford's law of digit bias to the Boston headquarters of the IRS. It is the only talk I've ever given where I've known ahead of time that there are agents in the room with guns. It's a slightly different feeling when you're giving a lecture, as well as people who could choose to audit me if I did a bad job. They are very proud of the fact that Al Capone was caught for tax fraud. That's how he was brought down. We care greatly about how quickly things converge. And we haven't talked too much about that in this class. I've mentioned the Berry Essen theorem, but if the IRS, if you want to pull the trigger and audit somebody, you want to know, is this a good thing to do? You want to know how quickly should Benford's law set in. And this is why all this stuff about pi to the n, the Fibonacci's, how quickly these things converge, that's why this is so important. Alright, so again, if anybody wants to talk more about stuff like this, let me know. I'm trying to balance the theory and the applications. This is great because this reviews a lot of material we've seen, and does theory, and does applications.